Today's lesson is going to be on calculating with moles of a compound. So we've already worked on mole calculations before with elements. And so today is just going to be an extension of those calculations that you've already learned, but this time we're going to be using compounds instead of elements. So for this lesson, you're going to want to have your periodic table and your mole diagram, and we'll be working on pages 8 and 9 and 10 of the class notes. We're also going to do a brief lesson on calculating percent composition at the end of this lesson. At any time during the lesson, go ahead and pause, especially at my prompts, so that you can fully set up the problems, solve them, and then check your answers with me. So let's get started. On page 8 of the notes, you'll see a picture of the mole as well as a series of one-step problems. So just like the first time around when we learned how to do mole calculations, we're going to start out with the easiest version. So we're given a sample calculation here in number 1 where we want to convert moles of a compound to mass of a compound. So we start our problem with the number that's given in the problem, right? Our 6.23 moles of sulfur trioxide. And using our good problem solving and setup skills, we're going to write number, unit, and chemical in each calculation, each portion of our calculation. Now, if we consult the mole diagram as a reminder to you, if I have moles and I want to get to mass, I'm going to follow this pathway where we go from moles to mass. And my conversion factor is going to be either the atomic formula or molecular mass. Now, atomic masses, when we were talking about elements, we looked those up in the periodic table. Formula masses and molecular masses are also looked up in the periodic table, but we have to use the mass of the entire compound, which means we have to add up the masses of all the elements present and the numbers of atoms of each. Okay, so in order to do that, we're going to start in this problem with SO3. All right, sulfur trioxide. We have to know how to write that formula correctly. So sulfur trioxide contains 1 sulfur and 3 oxygen. So from our periodic table, we see that the mass of sulfur is 32.07 grams per mole, and oxygen is 16 grams per mole. So to determine what we call the molecular mass or the molar mass, we're going to do 32.07, which is sulfur, plus 3 times 16.00. Okay, that allows us to calculate our molar mass. And we get 80.07. So I think this was probably we used a slightly different periodic table for that. But in any case, we're close enough. All right, so 80.07 grams of SO3 in 1 mole of SO3. So just like we used atomic masses with elements, we're using molecular masses with compounds. Our moles cancel, and we get our answer in grams. And like any math problem that we do, we're going to round to the correct number of sig figs in our answer. Okay, so let's look at another question together. So in question number 2, we're starting with 77.89 grams of calcium phosphate, and we want to know how many moles that is. So the first step in this process will be to write the formula for calcium phosphate. So remember using our knowledge of polyatomic ions and the use of the periodic table, we see that calcium is in group 2. And so therefore, its most common ion is a +2. So in this ionic compound, we have a calcium +2. And the phosphate from our memorization of polyatomic ions has a -3 charge. So in order to write the formula for calcium phosphate, we have calcium 3 phosphate 2. All right. So now we're going to set up our mole calculation. So we want to start with 77.89 grams of calcium phosphate. And we want to turn that into moles. Okay, so using our mole diagram, we have grams. We want to know moles. That's one conversion factor, which uses what we call the formula or the molecular mass. For an ionic compound, it's the formula mass. So we have to add up the mass of all the components in the formula. So calcium has a mass of 40.08, phosphorus 30.97, and oxygen 16. So I'm going to show that calculation of the formula mass or the molar mass. It's going to be 3 times the mass of calcium, 40.08, plus we have 2 phosphorus atoms total in our formula. So that's going to be 2 times 30.97. And then we have a total of 2 times 4, or 8 oxygen atoms, each with a mass of 16. So if we add up the molar mass of calcium phosphate, we have 3 times 40.08 plus 2 times 30.97 plus 8 times 16. Okay, that gives us a molar mass of 310.18 grams per mole. So using our molar mass that we calculated, 310.18 grams per mole, I'm going to use that as a conversion factor. 310.18 grams of calcium phosphate per 1 mole. Now, solving this on the calculator, 77.89 divided by 310.18 gives us 0.2511. We have 4 sig figs in our answer. 0.2511 moles of calcium phosphate. So that's all there is to a one-step problem. You're going to write the formula for the substance, the compound that you're interested in. You're going to set up a mole calculation using your mole diagram. And then you're going to calculate a formula or molecular mass, if necessary, to use in the problem. All right, let's look at number 3. How many formula units are represented by 6.50 moles of magnesium acetate? The first step, write the formula for magnesium acetate. Magnesium is in group 2 of the periodic table. Therefore, it has a +2 charge. The acetate ion, we know from memorizing our polyatomics, has a -1 charge. We write the formula. We need 2 acetates for every magnesium. So Mg C2H3O2 2. Right? Remember, with a polyatomic ion, you keep all the subscripts as part of the ion. You put it in parentheses, and then you use another subscript to indicate how many of those ions are present in the compound. So we're starting with 6.50 moles of magnesium acetate. So this is good practice for writing formulas as well. And using my mole diagram, I want to go from moles to formula units. So as you look at your mole diagram, you'll see that formula units are how we designate particles of ionic compounds. Right? So we're going to use Avogadro's number as our conversion factor for this mole problem. So there are 6.022 times 10 to the 23rd formula units in 1 mole of magnesium acetate. Okay, we're going to be canceling moles and moles. And we're going to end up with an answer in formula units, which is what we desire here. So you can see in this problem, there was no need to calculate a formula mass, right? Because we aren't dealing with grams at all in this problem. So all we need that remains here is to plug this into our calculator. 6.5 times 6.022, second function EE23. Okay, remember that sequence to enter scientific notation in your calculator. And we get 3.91 times 10 to the 24. 3.91 times 10 to the 24 formula units of magnesium acetate. And that's our answer. We pay attention to sig figs, we pay attention to units, and we pay attention to the chemical formula for each problem. So you can go ahead now and try number 4 and number 5, and you'll be able to check your answers in Schoology to those 2 problems. We're going to go on together now to work on some 2-step problems. So just one additional step from what we just did. How many ammonia molecules are there in 393.2 grams of ammonia? Okay, so the formula for ammonia is a common name. It does not follow either of our naming systems. Okay, so ammonia is kind of one chemical which you're required to memorize its formula. So I give it to you here because this is a sample problem. Ammonia is NH3. So I want to know if I have 393.2 grams of ammonia, how many molecules of ammonia do I have? Ammonia is a molecular compound. So when I look at my mole diagram, I see I am at grams of ammonia, and I want to get down here to molecules of ammonia. So I have to take 2 steps to get there. I'm going to convert grams to moles using molecular mass, and then I'm going to convert mass to molecules using Avogadro's number as my conversion factor. So let's set that up. We have grams. We've calculated the molecular mass of NH3. Nitrogen has a mass of 14.01. We have 3 hydrogen atoms, each with a mass of 1.01. So that's where my 17.04 grams per mole comes from. Okay, that's called my molecular or molar mass. So if I use molar mass as a conversion factor, I will have then converted my grams to moles. And then the last step is to use Avogadro's number to get the number of molecules. Again, moles will cancel, and then we have 4 sig figs in our answer. So the steps here remain the same. write the formula of the compound, use the mole diagram to decide how you're going to set up the solution, and if necessary, calculate a molar mass. Okay, let's look at number 7 together. What volume will 5 times 10 to the 22 molecules of carbon-4 oxide occupy at STP? Okay, carbon-4. So Roman numeral 4 tells me that carbon has an oxidation number of +4. Oxide, oxygen is always a -2. Okay, so we need 2 oxides for every 1 carbon. And so you should know that carbon-4 oxide, carbon dioxide. Okay, so if you did the crisscross method here, you would get C2O4, which then gets reduced down to carbon dioxide. Okay, now let's think about how we're going to set this problem up. We want to know volume, and we're starting with molecules. So we're starting down here, number of molecules, and we want to get to volume of a gas at STP, which is up here. So we have 1, 2 conversions to do. First, we turn our particles, our molecules into moles, and then we turn our moles into cubic decimeters at STP. That's what our volume is. Okay, so let's set that problem up. We have 5.00 times 10 to the 22 molecules of CO2. We're going to use Avogadro's number, so we know that there are 6.022 times 10 to the 23rd molecules per 1 mole of CO2. Molecules are going to cancel. And then our second conversion factor to go from moles to volume, 1 mole of CO2 corresponds to 22.414 cubic decimeters of CO2. That's called the molar volume of a gas. Moles will cancel, and we'll go ahead and do this math problem together. Okay, so we have 5 times 10 to the 22 divided by Avogadro's number, 6.022, second function EE23. Oh, actually, I brought my answer down from before, so let me start over. 5 times 10 to the 22 divided by 6.022 times 10 to the 23 times 22.414. So check that on your calculator, but I have 1.86 cubic decimeters of CO2, which sounds reasonable to me. So 1 mole of CO2 is 22.414, and you can see right here that we have much less than a mole, okay? So that, I like to sort of think through that. Does that make sense? Does my answer make numerical sense at the end? All right, let's try one more together. Number 8. How many grams are represented by 2.50 liters of sulfur hexafluoride at STP? So I have liters, I want to get to grams. Sulfur hexafluoride. So sulfur hexa is 6. So this is using that Greek prefix naming system. Sulfur hexafluoride would be SF6. 2.50 liters, SF6. All right. We're at volume. We're at volume of SF6. We want to know grams of SF6. So we need a 2-step problem, 2 conversion problems. First, we use the molar volume of a gas to get to moles. Then we use the molecular mass or the molar mass of SF6 to get to grams. So there are 22.414 liters per 1 mole of SF6. Liters cancel. Now I want to get to grams. Okay, so I need a molar mass. So sulfur, 32.07. Fluorine is 19. So we have 32.07 plus 6 times 19. 146.07 is our molar mass. Grams of SF6 per mole. Of SF6 per 1 mole. Our moles are going to cancel, and then we solve for our answer. 2.5 divided by 22.414 times 146.07. And I get 16.3 grams of SF6. And that doesn't sound like an outrageous number either. If there's 146 grams in a mole, and I have about 1/10 of a mole here, 16.3 makes mathematical sense. And so number 9 is another opportunity for you to practice on your own. Again, these answers are going to be posted in Schoology for you. So if you want to practice those additional problems in your class notes, those are available to you. And you should be all set to do the assorted mole problems that are assigned in your homework. So before we end this lesson, I'm just going to tack on one more idea for you, and that's the idea of percent composition. So if you'll turn to page 10 in your class notes, we're going to talk about percent composition. If I were to ask you what percent of our class is male, how would you solve that problem? So you would count up the number of males in the class. We have 3 in our class. And then we would put that over the total number of students, which is 15, and multiply by 100 to get the percentage. Okay, so that would be a way of expressing by counting how many males are in the classroom. Now, a different question I might ask you is, what percentage of our classroom by mass is male? Okay, not by number, but by mass. So how would we solve that problem? Percent male by mass, right? So we would get a big scale and we would mass all the males, right? Mass of males over mass of everyone. We would need a really big scale, and we're not going to do this, times 100. Okay, so that's called percent composition by mass. So this applies to in chemistry as well, because we can talk about any compound and calculate the amount of that compound that is made up of a particular element. And so we're going to do a problem here to demonstrate it. Okay, so in number 1, we want to know of the formula, whatever this is, magnesium chloride, we call this hexahydrate. It's a very weird looking formula, but this is the formula we're going to work with. I want to know the percent of water in that compound. So percent of water is going to equal the mass of the water over the total mass times 100. And it says to calculate this to 4 sig figs in this problem. So let's talk about how we're going to do that. So when we look at this formula, this 6 out in front tells me there's 6 water molecules associated with 1 MgCl2. So it's 6 times 2, it's 12 hydrogen and 6 oxygen. So the mass of water is going to be 12 times the mass of hydrogen plus 6 times the mass of oxygen, O. That's going to be the mass of water represented in this formula. The total mass of the formula is going to be all the water, again, plus the mass of the magnesium, which is 24.31 in the periodic table, plus 2 times the mass of chlorine, 35.45. All of that times 100. Okay, so the numerator represents just the mass of the water, and the denominator represents the mass of everything in the formula, including the water. All right, so I'll give you a chance to go ahead and calculate that, and we'll see if we come up with the same answer here. And I'm just gonna ask you to pause and do that calculation. So to report that answer to 4 sig figs, I have 53.17%. So you want to check and make sure that that answer matches your calculation. All right, we'll do one more practice together. In number 2, it says iron is mined from the earth as iron ore. We have 3 possible common ores listed here, and we wanted to know which ore has the highest iron content by percentage mass. Okay, and we'll calculate that to 3 sig figs. So you're going to have to calculate the percent iron in Fe2O3. So that would be the mass of Fe over the mass of Fe2O3 times 100. And you would do that for each of the ores listed here. Okay, so you would do that 3 times. So A, B, and C, and then you would compare them to each other. So we'll just set up one of these together. In Fe2O3, we have 2 iron ions, each one with a mass of 55.85 from the periodic table. And then we do that over the total. So we have 2 iron ions plus 3 oxide ions times 100. Okay, and then if you've done that on your calculator to 3 sig figs, I have 69.9% iron. All right, so check that against your calculations. And then you can carry out B and C, and you can pick the one that has the highest iron content from those. And this answer also will be posted on Schoology for you. So that wraps up our lesson on mole calculations and an introduction to percent composition. You should be all set and well prepared for working on the homework on these topics.